Well, good morning, everyone, and welcome to the second part of this cycle of conferences that brings together under the title Chemistry, a Hand Outreach to Society, 11 talks related to chemistry, chemical engineering, and biochemistry. Today, on this fifth talk of this semester, we will have the pleasure of listening to Fatima Garcia Melo from the Organic Department, who will talk to us about working together organic synthesis and on-surface chemistry towards the generation of unknown molecules, acenes and cyclacenes. As I tried to mention when introducing these talks, we opt for the online format instead of the face-to-face in the pandemic context, taking advantage of the platform provided by the Foundation General of the UCM, whom I would like to thank once again for their help and support in organizing this activity. This format enables many more people to be connected. I thank also to our funding sources, the Spanish Biochemistry and Molecular Biology Society, the Royal Chemistry Society, and the Vice Rector for Research and Transfer for the financial support. The choice of the language for this activity deals with the fact that the science is mainly written and discussed in English. Our junior researchers joined our institution after spending time abroad. Organizing these webinars in English can even make it easier for them to communicate their scientific results. In this way, we can extend our audience to foreign institutions, some of which have been the host institutions of these researchers. The lectures will always take place on Thursday at 12:30, and the last one will be on June 2nd, and each webinar will be announced at the beginning of the week, including the link of the registration form. Without further ado, I will hand over to the moderator of this talk, José Santos Barahona, professor of the Organic Department and also a speaker in this cycle of webinars. Professor Santos Barahona will introduce the speaker and moderate the questions that you can write in the preguntas and respuestas box at the bottom of your screen. Professor Santos, is your turn.
Well, thank you, Maite, for organizing this cycle of conferences. Well, today I'm quite pleased to introduce Fatima Garcia. I first met her in about 2009 when she was starting her PhD in the Department of Organic Chemistry of this faculty. She committed her thesis with Luis Sanchez from this department. She worked on submolecular polymers, and also during her PhD, she committed an internship in Eindhoven Technological University with Manmade. Thereafter, after finishing her PhD, she moved to Holland to take her first postdoctoral position at I had to read this, Wageningen University. She stayed there for about 2 years, researching with Martin Smulders, where she researched on dynamic covalent polymers for stimuli responsive materials. After finishing this postdoc, she moved back to Spain. She came to Santiago, University of Santiago at SICUS. There she researched with professors Diego Peña, Dolores Pérez, and Enrique Guitián. There she was a postdoc, but also she was granted with a Juan de la Cierva fellowship. She stayed there from 2016 and until 2021, and she was there working on conjugated polycyclic hydrocarbons. Since September 2021, we were very pleased to receive her in our department in chemistry. She got a position as lecturer in the organic department, and well, her scientific career can be resumed in. She's got about 33 articles, and which they have about 1,000 citations already. And her age index gives us an idea of the success of her research is about 21. Well, today Fatima, she will delight us with her talk. She's going to talk about on-surface synthesis of novel molecules. And well, Fatima, the floor is yours.
Well, thanks, Jose, for this very kind introduction. I'm very glad you were able to introduce myself. And yes, I'm going to share the... today I'm going to talk, because I joined the organic department in last September, so I'm going to talk about the research I've been doing before at FICUS at the Universidad de Santiago de Compostela. Is a mixture of organic synthesis and on-surface chemistry, so how these two areas together can be used in combination to reach novel architectures. So yeah, here I have a starting slide about the different size of objects we can find in the natural and in the artificial world. And since the first microscope was invented, researchers around the world have looked for new ways to stretch their understanding about especially first the microscopy world and then the nano and the subnano world. But yeah, if you have to be aware that depending on the size of the object you are looking at, you should use different type of tools to address their characteristics. And for example, for the micro world, which includes size from 100 nanometer till 100 microns to 1 microns, we can find this includes the size of cells or human hairs. We can use optical microscopes. But if we go down in size, above or below the length of the visible light, we cannot use optical microscopes anymore because they lack in resolution. So if we want to have a look at the nano world, which is the world below 100 nanometers, we have to use different microscopes. The objects that are in this size includes the objects, objects inside cells like enzymes or ribosomes or the DNA. But yeah, if we want to go to individual molecules or small molecules or atoms, we have to, as I said, use different tools. And in this regard, in the late 70s and early 80s, Binning and Rohrer broke new ground in the science of the very, very small with their invention of the scanning tunneling microscope. Well, this this instrument allowed the scientists to look at the very the very small, so down to small molecules and atoms. There was no existing technology at that time that allowed scientists to explore the surface electronic structure and imperfections, although for some applications, transmission electron microscopy is also it also works. Binning and Rohrer were awarded in 1986 with the Nobel Prize in Physics, just a few years later after their invention, which and which says that the high impact of this invention at that time. And well, the functioning, how does a STM, which is a scanning tunneling microscope, work? So you have a metal tip that you push very close to a sample which has to be conducting, and then if it's too close and you apply a voltage difference between the metal and the sample, or the other way around, tunneling electrons will pass through these two atoms, and this can be used to measure the properties of the sample and build an image of the surface. Here, for example, you can see the silicon atoms enlarged 20 million times, acquired by this technique. In 1986, Binning built the first atomic force microscopy, which was an offspring at first of the STM. This instrument allowed to visualize or to image surfaces which were not conductive. So the functioning work of this instrument is you have a nanoscale tip joined to a very flexible cantilever, and then once it scans the surface, if it's very close, depending on the force of the atoms in the tip with the ones in the surface, the cantilever bends. This bending is detected by a laser beam, and the position is detected through a photodetector. In this way, depending on the force between the tip and the surface, we can build an image about it. And this force is depending on the height of the surface in comparison. This force depends on the height of the surface. And so we can build an image of the height of the surface finally. Well, also the AFM and also the STM has allowed the really expansion of nanotechnology, because before there were not enough tools to really study the surface of atoms and small molecules. Well, here you can see, so on the left side, you see an STM. As you can see, this microscope is not really a tool that us as chemists can use as routine, in a routine way, because it's very, very complicated. So only specialized physics use them usually. And the AFM, it depends on the special equipment, because there are different types of equipment and setups, but this is a picture of the one we have in the facilities of the National Microscope Center at the Universidad Complutense. And well, here I put, so these were one of the first images that were recorded by STM by Binning and Rohrer, and here so they are silicon atoms. But we can not only visualize atoms, because you can push and pull atoms, you can also move them. And for example, one of the first examples was shown by IBM in this paper, where they manipulate xenon atoms and they construct their logo. A couple of years later, another authors were able to build a quantum coral of iron atoms. But to to visualize organic molecules that are absorbed on a metal surface is a very difficult task, because the electronic states that that are detected in the STM are how do you say? They are imaging atoms within organic molecules absorbed on a surface is difficult because the contrast is lacking in the states that determine the tunnel current. So here, for example, you can see an STM image of a pentacene molecule. But in 2009, the group of Leo Gross in IBM, they defined, or they invented a new way to image these organic molecules, and it was functionalize the atomic fork microscope tip with a small molecule such as carbon monoxide, which was put functionalized in situ. And here you can see the difference in resolution, in the high resolution that was achieved in this way. Also, with this tool, they were able to also scan surfaces that were not insulators instead of conducting metals. But moreover, because they can, so this area of research has expanded a lot, and even you can find in the IBM group that they have made a movie about it. So the A Boy and His Atom is called. So and these all points that you see here are individual atoms. Also, for example, I want to show you this example in which you see the movement of a silicon defect in a graphene sheet. But we can also have fun with science. And for example, they do every year the nanocar race, in which the different teams, they build a nanocar, which and then they have a race between the different molecules. And for example, this year, this nanocar, which is called NanoISPA, was designed and built and synthesized in the IMDEA Nanociencia Institute in Madrid, and it was done by Dr. Emilio Pérez Group and David Écija, and they won this race. So if you have any curiosity, you can have a look at the video. Well, but moreover, but more than visualizing or manipulating individual atoms or molecules, we can also think of doing reactions on a surface. And thanks to the development of these microscopes. And here you can see the idea. So the idea is to deposit molecules into this the surface in a surface on the STM microscope, and then perform a reaction. And in this table, you can see the different kind of reactions that were performed on a surface at that time. So this was in 2015. There are quite more already, including the Lasalle reaction. But the nice thing about this also, so this new area is called on-surface synthesis, and for me the nice thing is, or the interesting thing is that we have different reactivity in this. So the reactivity can be the same, or it can also be different. For example, if you think about the Ullmann coupling, the Ullmann coupling is not a very popular reaction in solution synthesis, but on the other part, in this, if you perform this reaction on a surface, is very efficient and selective. So we can find either different reactivity if we perform reactions in this way. And now I want to introduce you the next. So what are acenes, which is in the title of my talk, and yeah, the definition of acene is that they are polycyclic aromatic hydrocarbons which consist of fused benzene rings in a rectilinear arrangement. Here you can see the series of the acenes, so being the smallest one, the benzene. In 1972, Edith Clark proposed the rule to the Clark rule which was empirical, to predict the stability and the reactivity of polyaromatic hydrocarbons. First, we have to define what is a Clark sextet, which is 6p electrons in a benzene ring, which is depicted as a circle. And this rule states that the resonance structure of polyaromatic hydrocarbons is the one that has the largest number of Clark sextet is the most important for the characterization of the properties of this molecule. If we look into detail in the acene series, we can only draw one Clark sextet, regardless the number of units that it has, well, I will go to that later. Why are they interesting? Well, acenes, as we go down in the series, is interesting that the electronic gap decreases. Here you have the electronic gap for silicon, which is the archetype semiconductor which is 1.14, and for example, if you look to pentacene, which is the we see that is 2.21, which is quite low in comparison with naphthalene. The importance of this feature can be addressed by the high number of patents in which pentacene is used as the active layer of OFETs. But a drawback of this is that upon we decrease the number upon we increase the number of units, also its stability decreases. This is thought to be related with the number of Clark sextet, which is just one, regardless the number of benzene fused rings. Well, our approach to yield, so high acenes were only acenes up to hexacene can be synthesized by normal methodologies or traditional wet chemistry, but only heptacene and octacene and nonacene were detected. But still, it's thought that higher acenes are searched, but little success has been done in this area. So our approach to this, so the idea of the project was to synthesize a stable molecule in solution, which has multiple Clark sextet. In this case, we select the epoxyacenes, and then by on-surface chemistry, obtain the corresponding acenes. Why we want to do this? Because, well, this reaction, this deoxygenation reaction in solution, it has plenty of methodologies, as you can see here, but it was not known yet on a surface. But because the high acenes will be reactive and unstable, we thought that performing this reaction in very stable conditions, that like the ones that are held in the STM, like ultra-high vacuum and absence of oxygens, will lead to their stabilization. So this was done in collaboration with the group of Professor Francesca Moresco at the University of Dresden. Well, so first we had to synthesize in the lab these epoxyacenes, so these kind of molecules, and our idea was to perform this reaction via a Diels-Alder cycloaddition between an aryne and isobenzofurane. Diels-Alder cycloadditions are very important. It's a very important reaction in organic synthesis, because you make two carbon-carbon bonds in just one reaction step. So first we have to generate the corresponding aryne, which arynes are neutral reaction intermediates, so they cannot be isolated. So we have to generate them in situ, and we generate them from the ortho-trimethylsilyl benzyl triflate in the presence of a fluoride source. So it reacts with the silicon, and this bond is broken, and the triflate finally is expelled, generating the corresponding aryne. For the generation of the isobenzofurane, we start from epoxy, from an epoxyacene. We react it with dipyridyl tetracene via Diels-Alder cycloaddition, and after an spontaneous extrusion of nitrogen and a retro Diels-Alder, generates the corresponding isobenzofurane. Well, so this approach was validated in the group by a previous former group, which was Jose Maria Alonso, which is also now assistant professor at the organic chemistry department, and he synthesized this deoxygenated tetracene, and after the physicists were able to generate tetracene on a copper 111 surface. After a voltage boost, applying a voltage boost. He also was able to demonstrate that hexacene was also able to be generated from this 3-epoxy hexacene in gold 111, but also on a passivated silicon surface. Well, now that we had I had these precedents, my objective was, if this approach was also valid, to obtain long acenes which were thought or were not yet obtained or detected. So the higher one that was not yet, so the first one that was not yet detected at that time was decacene. So we design this tetra epoxy decacene, which you can see that bears 4 Clark sextets, so it should be stable in solution. And then we want to synthesize them, and from these building blocks. This includes arynes, as you can see here, or the cumulonic form of an aryne, or dienes or furans. Okay, so for the synthesis, we follow this synthetic route that is shown here. I'm not going to go really into the details, but you can see that the synthesis involves 3 reaction steps and involves 4 + 2 Diels-Alder cycloaddition. And finally, we were able to isolate in a 33% yield tetraepoxy decacene. And I want to show you that this molecule can exist as 8 possible different diastomers that you can see here, depending on the relative position on the oxygen, on the oxygens. Well, once we had in our hands the molecule, we sent to our to Francesca Moresco's group in University of Dresden, and they were able to deoxygenate the decacene. Here, this is the STM image, either by applying a voltage pulse or either by annealing the surface. In this right image, you can see a high resolution image of the with a tip functionalized with carbon monoxide, which is very clear that you see the 10 benzene rings fused in a row. But moreover, with the STM, if you do a spectroscopy, you can also have information about the energy of the orbitals of the molecule. And they were able to assign a gap of 1.17 electron volts for this decacene, which is quite low. So it's, it would be a good semiconducting species. Well, but some time after we published these results, two different groups were able to obtain undecacene. So first was the Echavarren's group, which they also used the on-surface chemistry to generate finally the acene, and it was obtained from a hydroacene precursor. Also, the Bettinger group, they were also able to detect the undecacene, and in this time they used the diketo precursor, and they irradiated on a polystyrene matrix at cryogenic temperatures, and they were able to detect it by the UV and near-infrared spectra. But well, we tried to push it further, so we wanted to increase the length of our epoxyacene, and this was done with Saleta Fernandez, which was a master student at the group. And so this was just including an extra reaction step. So we include an extra dilyl reaction from intermediate 8. And finally, she was able to obtain a pentaepoxy dodecacene in a 37% yield. This reaction route, or this synthetic route, involved 4 steps and 5 cycloaddition reactions. Also, the physicists were able to generate dodecacene by annealing the surface at 220 degrees, and by scanning the surface, they were able to obtain this image of dodecacene, which shows the 12 benzene units in a row. This is to date the record in length of an acene that has been detected. Well, but what is more, quite surprising is that when they measure the spectroscopy and they measure the electronic gap, is that for this dodecacene, so the electronic gap does not follow the trend of the other acenes, so it's higher than it should be, and we think that this is due to the higher contribution of the resonance structures possessing the radical character. But it would be very interesting to show what happens above this length. So if it does follow the trend or not. Okay, I want to, so this is a bit of an outlook. So to show the increase in complexity of the solution synthesis upon we increase the length of these epoxyacenes, for example, for the dodecacenes. So it involved 5 cycloaddition reactions in 4 reaction steps, but they can exist as 32 diastomers. So this really difficults the purification and the isolation of this molecule and decreases a lot the yield. So we have to, so if we want to go further, for example, for the 14 epoxyacene, we will have 62 4 diastomers, and this makes a bit very difficult its isolation. So we are looking into different approaches to do this. But well, after this, we thought if this approach would be also working for cyclic structures. So we hypothesize if we have a cyclic epoxyacene precursor, we could have a cyclacene. So, well, I want to talk to you about a little about what are cyclacenes. So first, carbon nanobelts are macrocyclic double-stranded molecules in which they are very interesting because they have their p orbitals are pointing the inner cavity inside of being perpendicular to the cavity. This is thought to bear very different and interesting physical properties to the molecules. So in the case, we have 2 types of carbon nanobelts. So would be the cyclacenes, in which the benzene units are ortho fused, and you can visualize them as the smallest or the narrowest part of a zigzag carbon nanotube. We can also visualize as a cyclic acene, but if you look into detail, it lacks in any Clark sextet. So this means, this hypothesized that maybe they are not stable at all. On the other part, cyclophenacines are this kind of belts, which are the smallest unit of an armchair carbon nanobelt. As you can see here, half of the benzene rings will have a Clark sextet, so they are thought to be much more stable. Well, carbon nanobelts have fascinated chemists for decades. So the first attempt for a carbon nanobelt was performed by Wittig in the late 50s, and he tried to generate from hexaphenyl, but this was not this didn't work. So here I show many attempts that were done to reach them, but unfortunately not successful. In 2017, cyclophenacene was synthesized for the first time, and this was performed by Itami, and he obtained by Wittig reaction this precursor, which were furthermore by coupling reactions yield, or Yamamoto coupling reactions, the carbon nanobelt. So this is, and also they were able to have a crystal structure, and it's a beautiful molecule. So cyclophenacines were obtained, but for cyclacenes were not a lot of success. The first attempt was performed by Stoddard in the 80s, and he synthesized this very beautiful molecule. But the last step, which is a Birch reduction, didn't work. Also, Corey tried to synthesize the 8-cyclacene, but also without success. So our approach was to synthesize the cyclic equivalents of our epoxy cyclacenes, and we designed these 2 tetra-epoxy cyclacenes. The one consisted of 8 units, and the one consisted of the bigger one with 10 units. For the synthesis of the bigger one, we planned a 2 retrosynthetic analysis in which two homotopic monomers were used, an AA and a BB type monomer. This would allow to, if we change the size of these monomers, we could, in principle, vary the size of the final epoxy cyclacene. So I'm not going to go into details of the synthesis, but it's the same idea as for the linear acid. So we just perform Diels-Alder cycloaddition reactions between furenes and arynes. And finally, we were able to obtain the cyclic epoxyacene 20, and this structure was confirmed by X-ray diffraction. So we sent these molecules to Leo Gross group in IBM, and they were able to deposit on copper 111 surface. And first, when they deposit at low temperature, you can see that the molecule, so these are AFM images at different height, and you can see that here that the benzene ring is parallel to the surface, so the molecule is upstanding. This protuberance, so these brighter dots correspond to the oxygens, which are higher. After they anneal the sample, what they found are self-assembled islands. So the way the molecule interacts with the surface has changed a lot. So now the molecules are, so the cavity is standing in the surface. This, for example, these bright dots that you see here are the hydrogens coming from the benzene rings, which are pointing perpendicular to the surface, and thus are higher. Well, after they were able to deposit and visualize these molecules, because they are not planar, so they have three-dimensional structure, and this is very difficult for them to visualize and assign what they are seeing. So they were they had a lot of success with this, but then they tried to do the oxygenation, and what they did is they increased the voltage. And so here you can see an image of the AFM after increasing the voltage on the lower part, and you can see that we can see some difference. In this yellow box, you can see a pristine molecule. So what we had, so the pristine molecules without any deoxygenation, and you can see some different structures. So, for example, you can see this blue chart. You see that is two oxygens are gone, so this is more planar, and you see that the curvature has changed a lot. Also, we were able to see this structure where the two other oxygens have been removed. But upon increasing more the voltage, it was not possible to find any to remove completely the four oxygens. And this is related, we think, with the high energy that is needed, because upon removing the oxygens, the curvature, so the strain of the curvature is very high, and then the molecule breaks before reacting. Well, that's all. I want to thank my group in Santiago, Professor Diego Peña, Professor Enrique Guitián, and Professor Dolores Pérez for their support. and the funding and our collaborators, Francesca Moresco and Leo Gross, and all of you for your kind attention. Thanks.
Thank you, Fatima. It's been very, very enlightening talk, this one you have given. What is the first question I have is, what is the usual temperature you use for the position of the molecules on top of the surface?
Well, it depends. For the acenes, it depends on the molecule because they have to sublime. So they need to sublime it from the surface. So it depends. So as the molecular weight increases, you need higher temperatures to deposit. I cannot recall exactly the temperatures that were used, but that's the case for the acenes. So
sorry, Fatima, you misunderstood me. I'm not asking about the temperature of sublimation, but the temperature of the surface where they are deposited on top of. I mean,
in the case of the cyclacenes, it's room temperature, but this is a very special. I think so. I'm not I'm not a specialist in this, but it's a very special technique that they have in IBM that they are able to deposit at room temperature.
All right.
But for the acenes, I cannot recall the number.
Right. Yeah, I was just wondering because sometimes you can observe differences in reactivity, whether you use room temperature or even higher temperatures or lower.
Can I ask a question? I mean, I have a question, a very general question that I want to ask Fatima. I mean, which is the uses that you can do of these molecules? I mean, because you say that there are a lot of patents in this kind of materials. Then, which is the uses that you can do to this kind of material? So which are the applications that you can use for this kind of material?
So anytime you have an organic semiconductor, it has a lot of applications in any application that there is a semiconductor, if you can use organic molecules, it will give flexibility in principle to the device. And also, depending on the application, so it is said that organic molecules can be processed in a cheapest or way, but I don't think it's the case for decacene, of course. So this is very fundamental research, but this is the trend for organic electronics. So replacing silicon, not replacing. So it's good if we have like a bunch of semiconductors, and depending on the application, we can use one or another, and then we just don't depend just in one raw material. So that's my point of view. But this is very fundamental research of how can we do new reactions and obtain unexpected or molecules with this combination of tools.
Yes, indeed, it's quite exciting. I have a question regarding the how do you cleave the epoxides? So you said that you're applying a voltage. I assume that you're applying the voltage with the tip of the microscope, but could this cleavage of the epoxide can be performed thermally, or
yes,
you have to go molecule by molecule?
No, indeed. For example, for the decacene, it also works thermally. And also for the dodecacene, but it was just for the cyclacenes that it was just done with the tip, because they are like more sensitive, let's say.
All right. Still, we don't have any questions from all the viewers. Please, I encourage you to send your questions. You can also ask them in Spanish. There's no problem with that. We will translate them. Meanwhile, I have another question for you. I've observed something really interesting with the dodecacene, because you got that the gap is widening, so it's opening. Have you ever tried to test or to calculate the topology of the nature of the topology of the atoms, or not of the atoms, of your molecules? Because from your graph, you can observe that how, as you go from benzene, let's say, up to pentacene, I think it was, the band gap is shrinking, it's getting reduced. And then when you pass, was it dodecacene? No? It was
Yes,
dodecacene?
yes.
Then it comes up again. This is something that you normally observe when you go through a phase transition, a topological phase transition from topologically trivial to non-trivial. So the band gap has to shrink, and then in order to because the orbitals, they get mixed, they have a crossing, you have to pass by a metallic state where the band gap is 0, and then you go up again, and the band gap begins to open. Have you considered studying this? Because this is quite a hot topic. I mean,
no, it goes out of my really my knowledge. I'm not so the physicists. So they perform a lot of measurements on the electronic affinity and the energy of the orbitals and all this, and they so they came up with an explanation with which I don't understand really, and but there's a lot of controversy why this is happening. So there are like different groups, the physicist groups that think it's because of different, so the causes are different. So it can be what you say, but I'm really not, I don't know, so sorry.
Well, if I were you, I would try to encourage your colleagues to go through this, because this has very nice potential applications. Any
Sure,
other
thanks.
questions? Maite, you have questions? I may have a last question, which is quite general. Do you think this technology or technique of surface chemistry can be at some time applied like in large scale? Because I assume that you have like very reduced areas where you can deposit the molecules. So the number of molecules you may have are quite reduced. So in order to have, let's say, applications towards some sort of device, we'll need a lot of molecules. So do you think at any point, any time in the future, this will be accessible?
Well, I think there are a lot of so the area is growing very fast, and especially how the molecules are deposited on the surface is a key issue. And in this regard, so now they are trying to electrospoon, or electrospoon is the tool, so the name of the setup. So it's like on a electrospray in a mass spec. So there, if you don't have to heat them and you don't need the ultra high vacuum, I think at some point you could do like in high areas. But at this point, not yet. But I really think it will be expanded to bigger areas.
I think that's will be the case where this will be very applicable, very like become a tool for our point of view, from our point of view as chemists. Well, we still don't have questions. We have some
Everything is
people
very clear.
congratulating you. They have liked your presentation.
It's very clear, and the people is very shy also.
Yes,
I think.
it's a pity.
Yeah, because I think that these seminars are useful to get a lot of questions of people that are more or less related with the topic and can find some kind of a synergic relations between the researchers. But I think that it's a problem with the people that is very shy
Yes.
in order to do the questions.
Well, you can also ask me if you find me in the corridor.
Of course, of course.
Sure.
Then Fatima is in the organic department, and everybody that wants to ask questions can go there and ask her the next months. Then it's all right. Well, then the only thing that I have to do is to thank Fatima for this nice talk, to thank also Jose for introduce her. Next talk is in April 21st. Is Ruben Aijado from the Chemical Physical Department is going to be to talk about plasmonic nanosensors. And to everybody, enjoy your Easter holidays, and see you in April 21st. Okay, then bye.